Today, we are looking at statistics and probability. The main goal in statistics is figuring out how to learn about a large group without having to track down every single member. We do that by examining a much smaller, manageable piece, which we call a sample. But first, we have to clarify what we mean by the word population. In geography class, population usually refers to a head count, the total number of people living in a specific city or country. In statistics, your population is simply the entire specific group you want to study. It could be all the oak trees in a forest or every 7th grader in your state. Understanding exactly who or what makes up your statistical population is the first step. Once you define the whole group, you can pick a sample to study, with the goal of drawing conclusions about the total group without having to survey every single individual. Let's look at a problem. A school wants to figure out how its students travel to campus each morning. To find out, the principal asks 50 randomly selected students. This massive school of glowing koi represents our population, all students at the school. The sample is the 50 selected students who answer the survey. We use this smaller, linked subset to understand the whole school, provided it's chosen fairly without favoring one group. Here is a different scenario. A student wants to know if the school should buy more sports equipment. They decide to survey only the members of the basketball team. Pause the video for a moment and think, what might the rest of the student body say compared to the basketball team? If you noticed a problem with that survey, you spotted what statisticians call bias. Statistical bias happens when a sample fails to reflect the diversity of the larger group, often leading to results that don't match the reality of the whole population. This animated scene shows a tiny group of energetic hares separated from a wide forest of turtles and badgers. If you only ask the hares, you isolate a group with specific interests. Because of this isolation, the survey is statistically biased. A useful sample must actually mirror the population it represents. Let's look at a final scenario. A town needs to estimate which features its residents want in the local park. The planners must decide between taking a sample or asking every single resident. This diagram shows a pine forest filled with thousands of squirrels. Surveying every single resident, taking a full census, requires a level of time and resources that many towns simply do not have. Counting every squirrel is a massive logistical challenge. A scientifically chosen, fair sample allows town planners to gather data that reflects the community's preferences. It estimates what residents want without reaching every single home. Modern statistics relies on collecting data in manageable chunks. This approach allows us to draw conclusions about the entire group while keeping the work of gathering information within reach. This diagram shows our two approaches side by side. On the left, the randomly selected koi fish provided a more balanced picture of the population. On the right, surveying only the hares created a biased sample. This brings us to a key rule for inference. A random sample is likely to be representative because the selection process is fair, giving every member a chance to be included. Before you practice these ideas on your own, consider this final question. Why does randomness help a sample better represent a diverse population?